Hello and welcome to Minukuu tutorials. In today's tutorial, I'm going to show you how to perform one sample t-test in R or R Studio. Now, for all subscribers of Minukuu tutorials, you would bear with me that I've already made videos on how to perform two sample t-tests, be it for paired or unpaired groups or samples. In this particular tutorial, like I said, we're going to look at one sample t-test. Now, the objective of a one sample t-test is to test or to determine whether an unknown population mean is statistically significantly different from a specific reference value. Okay, so at the moment you might not understand the purpose of t-test, but as we proceed I will explain to you the purpose of t-test in details. So I have my data set on the desktop in the form of a CSV file, and I've named it t-test data. We're going to read it into R and start. I've used the object BMI data as the name of my data set in R. Okay, but the data set itself is on the desktop and it's named t-test, and it's a CSV file. If you have difficulties in reading data into R, please check in my channel and you'd find many videos on how to read data into R without any problem. So I'll quickly run this code to read our data set into R. Perfect. And then it hasn't given us any error. Now to show you the data, I simply run, let me show you the data. Simply print the data, print BMI data, and this is our data set. So it's actually, this data set contains, it's a random sample drawn from a population of women who consume a particular weight loss drug. Okay, so now, for instance, let's assume that we are carrying out a pharmacoepidemiological study to determine the effectiveness of a particular drug in the real world. So now, this particular drug, like I said, is a weight loss drug and is consumed by women. Okay, now, though the drug has been approved into the market, we seek to know whether in real life the drug is really performing. Okay, so if the drug is made for weight loss, then what that means is when somebody takes the drug, his body mass index is supposed to decrease, right? So if we want to test the effectiveness of a drug, of such a drug, we could simply use t-test, one sample t-test for that matter, to determine whether the average body mass index of individuals who consume this particular drug in the real population is statistically significantly different from a particular reference value. In our example, we could assume that the generally accepted or if you want, the average body mass index of an adult is often 18.5. Just like if I say the average body temperature of a human being is 37 degrees Celsius. So it's conventional. Let's assume that it's conventionally known that the average body mass index of an individual, or if you want, of an adult, is 18.5. So now we would use this as our standard value, and then we will try to compare the mean body mass index of the population of people who consume this particular drug to this particular standard value. I repeat myself, we will compare, or through statistical testing. So because we cannot, if we could just go and measure the mean body mass index of the whole population of people who consume this drug, that's the whole population of women who consume this particular weight loss drug, that would have been perfect, but it would be time consuming because you have to employ a lot of people to be able to count all the people in this world who consume this drug, to be able to determine the population size and after which you have to waste your time calculating the body mass index of each and every member of this population before you can come out with the average body mass index of this population, so that you can just have it and just compare it to your reference value or your standard mean body mass index that we are assuming to be 18.5. But since we cannot do this, then it means we have to resort to sampling. So we have decided that, okay, we're going to draw a random sample of 20 women who consume this particular drug from the real population. It's a random sample that we've drawn. And now from, if at least we are able to calculate the mean of this particular, what do you call it? If at least knowing the mean of this particular simple random sample that we've drawn, we will be able to deduce, even though we will not still be able to know the exact value of the population mean, but we'll be able to deduce whether the population mean of women who consume this particular drug, the population BMI mean of this of women who consume this particular drug will be statistically significantly different from the reference value that we are assuming to be what, 18.5. In which case, if it's greater than, then it means, sorry, if it's less than, then it means in the real world of people who consume this particular drug, women who consume this particular drug have significant weight loss, which means the drug is actually efficient, considering the fact that the average body mass index of the population of women who consume this particular drug is less than the reference value. On the other hand, if the test shows that the average BMI of the population that consume this particular drug is greater than the reference value, which is 18.5, then at that point there are two things involved. It's either the drug is a risk factor, in other words, the drug increases the risk of gaining more weight, or there are other factors responsible for the weight gain and the drug is probably not efficient. At the same time, if the test proves that there is no any statistically significant difference, in other words, the body mass index of the population of women who consume this particular drug is not that much different from 18.5, then what that means is that the drug is inefficient. So this is the purpose of what a one sample t-test. It involves just a single population, and we seek to compare the mean of this particular population to a standard mean, or if you want a standard or reference value. This is the purpose. I hope my explanation is clear. If you still have any doubt or any misunderstanding about one sample t-test, please comment and I will reply you. Alright, so having read the data set into R, we'll start the test. But before starting the test, it's important to verify that the test conditions are satisfied. Remember that this is a one sample t-test, and every t-test is what? A parametric test. In other words, it's based on the assumption that the population distribution is what? Normal. The viability of our test results, of our one sample t-test result, is dependent upon the normality of the population distribution or population of interest. In this case, we must verify that the body mass indexes of the population of women who consume this particular drug is normally distributed. In other words, it follows the Gaussian distribution law. Otherwise, we will be obliged to perform a non-parametric test, which does not require that the distribution of the population follows what? A Gaussian law. And the non-parametric test for a one sample t-test is what? The Wilcoxon one sample rank test. Another test that we could have performed in place of one sample t-test would have been the z-test. However, the z-test requires knowing the population standard deviation or variance, which is often not the case We cannot, often than not, we don't know the population standard deviation, and that's why it's preferable to do t-test. But if you have to run a t-test, then you must also verify that at least the population of interest follows a normal distribution. Now, how do we test that? There are several methods. Some people simply plot a histogram of the population, of the sample distribution, and they assume that if the sample distribution, if the histogram is more or less like, it's well uniform, more or less like a pyramid, then they assume that, it suggests that the population distribution will be what? Will be normal. Some people use QQ plot, and the best option for me is to do the Shapiro-Wilks test of normality. And I'm going to quickly show you these two methods, and then we will move on. Now, to test the normality of our population distribution using the QQ plot, we'll need a package called what? ggpubr. So you simply say install .packages to brackets, the quotations, then you write ggpubr. That's the name of the package. This package contains a code called the ggqq plot, and that enables us to do the QQ plot. Okay, so it's asking me to select what do you call it? My ground mirror. Since I'm currently living in Paris, so I'll pick France, Paris 1. Okay, and just for your information, if you ever come to Paris, make sure you holler your boy. I'm right here. Please look for me. Okay, all right. So the installation is in process. Perfect, the installation is done. And now we're going to load our package by simply saying library into brackets ggpubr. In order to load our package, what is it saying? ggpubr library. Sorry, I made a mistake. Library. Look at how I spelled library. Library. Sorry, let me take it again. Perfect. Now our package is well loaded, and we'll move on to perform to plot our ggqq plot. So we simply say but before then, we have to make sure we attach our data set. Okay, let's attach our data set. I forgot to attach our data set after, so we have to attach our data set. Okay, now that we've attached our data set, let's move on to, as I showed you earlier on, let me print the data set again and show you. Our variable of interest here is what? Because we only calculate the mean of a numeric variable, and the numeric variable of interest here, so which means t-test, one sample t-test involves what? One numeric variable. Our one numeric variable of interest here is the BMI of each patient. In all, we have 20 patients, so we simply I've attached my data set so that if we want to select BMI, we don't have to say BMI data $sign BMI, so we can just write BMI straight. This is the purpose of attaching the data set. So now we'll go on and plot our QQ plot. So I simply say ggqq plot into brackets, then we say what? BMI. Perfect. And this is our GGQQ plot, or if you want simply our QQ plot. Now what this particular plot represents is what? It's a plot of the sample quantiles against certain theoretical quantiles generated by R. Okay, now, and it draws this diagonal line here, and the interpretation is simple. When you realize that the population distribution is said to be perfectly normal, when you realize that if not almost but majority of the points lie on this line here. In our case, not all the points are lying on the line, or at least it's only, I think, this particular point that we can see lying directly on the line. But it doesn't mean that our distribution is not normal. It's all about, the question is how perfectly normal the distribution is. So one other thing that we can help us do the interpretation is this kind of I don't know what to call it, this kind of the gray space here. Okay, when most of the points fall within this gray space, it means that your distribution is relatively normal, and in our case all the points are within this particular gray space here, spot here. You see, in addition to that, we realize that the points are actually very close and very close to the line, which suggests that we have a relatively normal distribution. But this might not still give you, an in-depth understanding, because this is a graphical representation sometimes. So you can, if you want to verify, to prove that, okay, what you are seeing graphically suggesting that your distribution is relatively normal, you can still verify this using a statistical test called the Shapiro-Wilks test of normality. Now let's do that one. It's very simple. We simply say Shapiro test. So let me get down here, and to do the Shapiro's test we need a package called car, C-A-R. So you say install .packages, into brackets, into quotations, you write what? CAR, close the quotation, close your bracket, and then you run this to install the package. It might take some time, but I hope that it will be installed. Okay, now that the installation is done, we load the package by simply saying what? Library into brackets CAR. Then we load our package. They are saying what? Loading required what? Package car data. So, which means we were supposed to install a package called car data before we can actually load this package. That is weird, but let me try again and see what it will say. Let me try loading again. It's now loaded, no problem. Let's go on. Now that the package is loaded, we're gonna do our Shapiro's test by simply saying Shapiro.test. Shapiro.test. I like the name Shapiro. .test into brackets what? BMI. BMI is our numeric variable of interest. So let me do this, and then the test is done. It has given us a p-value of what? 0.9. A p-value of 0.9 means that we cannot reject the null hypothesis. The null hypothesis suggests that our population distribution is similar, if not equal, to a normal distribution. So you see that we have a p-value that is largely greater than what? 0.05, which means we cannot reject the null hypothesis, which suggests that our population of women who actually consume this drug have their BMI distribution is relatively normal, and then which means we can perform our t-test without any problem. So let's do that. But before we perform the t-test, it's usually important that you explore your data. For instance, in two sample t-tests, it will be good that you use box plot so that you can compare the medians of the two groups in order to give you an idea on the kind of hypothesis that you can formulate, because the whole concept is that if we are assuming that the population distribution is normal, then what that means is that if the distribution is normal, then when we draw a random sample from this population, the result that we will see on our sample will be a true reflection of the population value, since the distribution of the population is normal and the sample was also randomly drawn. So if we calculate, though we might not, the sample mean will not be the exact value, the exact population mean, but this is the idea. So let's calculate the population mean, for instance. Sorry, the sample mean. So we just say mean of BMI. Now if I should run this, let's see what we get. This gives us a value of what? 18.4. So now remember, the hypothesis that I formulated was that I haven't yet formulated the hypothesis, but I was assuming that the what do we call it, the standard BMI value of reference that we are going to use, or the reference, or if you want, the standard BMI value that we are to use is what? 18.5. So we are assuming that generally the average adult body mass index is 18.5. So if our sample body mass index, average body mass index, is 18.4, this gives us an idea that since the sample distribution is normal, sorry, the population distribution is normal and our sample was randomly drawn, if we have 18.4, then this gives us an idea that no, then what that means is what that means is the true population mean, which we don't know, will also be will not be significantly different from 18.5. This is the whole, that's why we need to explore our data set first, and then before we move on to formulating our hypothesis. However, that depends on you. But if our sample mean were to be very, very less, let's assume we had 5, then we could have started suggesting that then if we have a sample mean of 5, then it means this, the population mean will be what? Of women who consume this particular drug will be relatively, will be less or far less than 18.5. But in our case, we are, as we can see, 18.4 and 18.5, there's no much difference. So though we don't know the population mean, but our hypothesis will be that. So null hypothesis H0 will be that population mean mean BMI is equal to 0. Sorry, I'm saying 0 is equal to 18.5. And then the alternative hypothesis H1 is that okay, the alternative hypothesis, let me just copy this because I don't want to waste time. So the alternative hypothesis is that it's either greater than or equal to, or you can say less than or greater than. I'm so sorry. It's either greater than or less than, but with, okay. Okay, which means now we can put our alpha to be, let's say, 0.05. 0.05. If our alpha is 0.05, then it means our confidence level will be 95%. And since we are saying it's because it's the null hypothesis that often carry the equal sign. So if we had said, for instance, that here we were assuming that the population mean will be less than or equal to 18.5, then the alternative hypothesis would be that the population mean BMI will be what? Greater than 18.5. And if this one were to just be greater than, then it means it will be a right-tailed test, which means greater. You get what I'm saying? It's a right-tailed test. But if it were to be less than, which means here we had said here is what? Greater than or less than, greater than or equal to 18.5, then the alternative hypothesis would be that it's actually less than 18.5, which would have been what? A left-tailed test. So we write less. You see this into details, so since in our case we said it's equal to, the opposite of equal to is what? Greater than or less than, which means it's a two-sided test. So this is two-sided, two-dot-sided, based on the alternative hypothesis. Now let's move on to performing the test. To perform the test is very simple. We're going to use the t.test command, t.test, and then to brackets we're going to write our variable of interest, which is BMI. We put comma, and then we have to specify our reference, or if you want, standard mean value. So we are saying that we are assuming that generally the average body mass index of an adult, of a normal adult, regardless of whether he's taking weight loss drug or not, of a normal adult, so we are talking about normal adult, is supposed to be what? 18.5. so MU here stands for this mean reference value, so, or standard value, which is equal to what? 18.5. Remember that when we were performing, in my previous videos, when we were performing two-sided test, MU here stood for what? The difference, the mean difference between the two populations. But in the one-sided test, it's not the difference between the means of the two populations, but it's rather the reference, or if you want, the standard mean value to which we are comparing our population mean. So it's 18.5, and then we have to also indicate what again? We have to indicate the alternative hypothesis. So it's either you say out or alternative. So we have to specify that our alternative hypothesis is actually a two-sided test. So we write into quotations two-dot-sided. We close the quotations, we put comma, and then we also have to indicate what again? The confidence level. By default, R assumes an alpha risk of 0.05 and a confidence level of what? 95%. But if you want to change it, that's up to you. So that one is not necessary, but we can still indicate it, that conf dot level, confidence level, is equal to what? 0.95. And now I think we can perform our test and then conclude. So if I should run this, the test statistic is minus what? 0.14, and then it gives us a p-value of 0.8. so this p-value is actually greater than 0.05, which means we cannot reject the null hypothesis, which suggests that the real population mean BMI of people who consume the particular weight loss drug is not that much different, or if you want, it's not significantly different from 18.5. In other words, it's equal to what? 18.5. And what that means is that our body weight loss drug is inefficient, considering that the test has proven that the average body mass index of the whole population of people or women who consume this particular drug, the average body mass index would not be significantly different, or in other words, not less than or greater than what? 18.5, which means it's equal to. But that doesn't also mean that, you know, we cannot really conclude. So we cannot conclude. Let's conclude. Our conclusion will be that we cannot conclude, or interpretation will be that we cannot conclude, considering that p-value is greater than 0.05, we cannot conclude that there is, we cannot conclude that the mean population BMI is significantly different from 18.5. And what that means is that, but that doesn't mean the drug is inefficient at this moment. We don't have enough. We still have to, you know, we will have to conduct our study on a larger sample, because the larger the sample, you know, the higher the test power. In our case, we just conducted our test on a sample of 20 people, women, and probably our test power is not enough to showcase this difference, or to showcase any possible difference that exists, you know, between the average body mass index of the people who consume this drug, or the population of people who consume this drug, and our reference average body mass index, which is 18.5. So we cannot conclude. Thank you so much for watching, and I hope this video helped. Please subscribe. Bye.